I don't know. I think people will find new ways to hurt themselves. So that even this is not going to save them.
I always say.
No, they go.
Yeah, I just want the super medical technology to get here sooner than later, so I can just, I could be awash in nanobots and never get sick.
Oh, okay.
Oh, so you know that.
Or you can just
I have their
move your consciousness
not
into
the
the cloud.
one, but it's
Yeah, I don't know about
information
that.
around
That
everything,
seems
and they're
risky.
grouping words, and then they're grouping
They say that's what we're
words.
doing now,
It's all
possibly.
hard before
Well, it's going to happen gradually, but then one day people will look back and go like, "Holy smokes, we're living on the internet now."
Yeah, but this one works for other places too. There's only one message.
Yeah.
All right, so I'm going to go ahead and get started today. It is 7:01 according to my watch. So today is going to be an interesting lecture, okay? And the lab portion may be structured depending on what kind of questions you have and whatnot. It all has to do with your next homework assignment, okay, which is already online on Moodle. And remember last time I kind of talked to you guys about, okay, your next homework assignment is probably going to be implementing the microcode of an add instruction and stuff like that. Well, guess what? That's part of your new homework assignment. Okay, so your new homework assignment is a little bit challenging, so I would encourage everybody to start early. I know Monday is a holiday and we don't have to be here, but since this class is a Tuesday, Thursday class, it does not impact us. In fact, it gives you one more day to do homework for this class. So, okay, but we'll take a look. Okay, we will take a look at the homework assignment, and we'll see how far we can get, explaining what it is and how to get it done. So it's about the control unit, and definitely we want to record today's lecture. Okay, that is going to be very important. Not really to the people who are missing today's class, which I will find out because I intend to take roll tonight. But it will be important to you guys as well. So even if you're here paying attention, there will be certain steps that you think, oh, okay, I just kind of missed that one step. Okay, so it will be useful. And as usual, the focus should be on why we're doing something, the overall concept. The details, since it's all getting recorded, you can ask me to check the recorder from time to time just to make sure I don't goof up. But the detail is going to be recorded. So focus on the big picture. Focus on how to do something, why we are doing it, and not really quite as much the details of which button do I click to get this done. Okay, because that's not going to be as important. All right. Oops, I just moved to a different screen. So it is in the control unit. It's called microcoding 1, which implies there might be a microcoding 2, 3. There will be sequels to the microcoding homework assignment. Those will come along when we start to write code in actual assembly programming language, so that we will look into the architecture and say, okay, so how do we implement a jump instruction, or how do we perform a compare instruction? So that way, not only are you learning how to write code in assembly code, but you also understand inside the processor what is happening when that particular instruction executes. Okay, so it will give you some context of what is happening inside the processor, along with the actual Intel architecture code. So let me click here first. I'm going to right-click and open a new tab because I think I'll have to kind of go back and forth a little bit. All right. So the homework assignment is this. Okay. The first part is to download my processor, which is actually right here. This is the zip file that you have to download. It's the same thing that I have been using for the past 2 classes at least. Okay. So if you have been experimenting with that, you have that already. So download that and start with it. And you want to maintain the directory structure. In other words, you want to keep all the files in the same folder. And then I'll talk about that later. You don't want to alter the processor design itself. Okay, so even though you can mess around with it if you want to, save it as a different file. So for the homework, for homework purposes, you want to use exactly the same design in the zip file. Don't change it. And here are the actual content. of the homework assignment. The first one is to utilize a new opcode. This one has not been used yet, okay? So utilize this opcode to implement a CP indirect register instruction. So what this instruction is going to do is the instruction will specify one of the 4 registers in the register bank as the source register. And the source register will be copied to the indirect register, and that's it. That's the whole instruction. Okay, that's the whole purpose of this instruction. And that's why it's called CPINDIR, because it's just copying the content of one of the 4 registers in the register bank to the indirect register. Okay, so I will show you the picture later on and kind of give you some clue of how to get started with this. The second instruction that you'll be implementing is going to be a load indirect register. So what this instruction is going to do is you have to specify, the instruction will specify a destination register, and the destination register will store the content that is pointed to by INDIR, or the indirect register, in RAM. Okay, so it's a 2-stage thing. The previous instruction will set up the indirect register, and then this instruction will utilize the indirect register, which is not one of the 4 in the register bank, in order to go to a particular location in memory, get the content, and then store it in one of the 4 registers in the register bank. Are we doing okay so far? Now, there's a reason why I cannot combine these 2 into a single instruction, and it has to do with the limitation of the architecture itself. I will show you why that is the case, because as I explain why it cannot be implemented into one single instruction, you will be able to get some idea of how to implement these 2 instructions. The third instruction that you are going to implement is the add instruction. Okay, the add instruction is going to specify 2 registers as operands. In other words, you'll be using the least significant 4 bits, the X, X, Y, Y, to specify 2 registers. Those 2 registers will be added using the ALU. The sum of the addition is going to be stored into one of the 2 registers. And it will be clear which register has to be the one that is storing, because only one of the 2 registers can serve both as the output from the register bank and also to serve as the input into the register bank. So it has to be that one register being the destination register. The second register is just going to be a source, basically supplying a bit pattern to be added to the other one. Okay. So those are the 3 registers or 3 instructions that you're going to implement. And then you're going to write some code to test it, right? So in order to test it, this is the program that you're going to write. So I'll just kind of briefly explain, what you have to do here, and then we'll go straight into the processor design, and I'll give myself, a particular instruction to implement so that you guys can see the process of doing it. Okay, so the first thing you have to do is to hard code 2 memory locations to a certain value, okay, because you want to test whether the addition is working or not. So we're going to have to program those 2 locations. So location 20 in hexadecimal, when you see 0x as a prefix, it means that number is in base 16. Okay. So at location 0x20, 20 in hexadecimal, we want to store the value 56 in hexadecimal. At location 21, we want to store the value 8a in hexadecimal. Okay. That is easily done. You just go to the RAM chip, go pop up the editor, go to those 2 locations, type in the values, you're done with it. Okay? I'll show you guys how to do it using the tool, using LogicSim. At RAM location 00 and 01, because it takes 2 locations to specify this kind of instruction, you're going to write an instruction to load a constant, a particular value of 20 in hexadecimal into register A. That instruction is already implemented. Okay, so it's already here. I'll show you guys exactly which instruction I'm talking about and how to specify the value as well as the register. You will use about the same kind of instruction, except in this case, you use location 2 and location 3 to write an instruction to load the value 21 in hexadecimal into register B of the register bank. Are we still doing okay so far? Okay. So I'm basically setting up for the other instructions at this point. The next instruction at location 4 in RAM is an instruction is this particular instruction. So this is one of the instructions that you are going to implement. It is the CPINDIR of copy to indirect instruction. So you'll be copying the content of register A, which we loaded up a little bit earlier, into the indirect register. Okay, so that's going to utilize one of your instructions. At RAM location 5, we are going to utilize the load INDIR or load indirect instruction, so that we'll be loading the content of one location in RAM using INDIR reg as a pointer into register C. Okay, any questions? I can give you the pseudo C equivalent of this code, just so that you can see from the C perspective what we are actually doing. At RAM location 6, we will write an instruction to copy INDIR, copy into the indirect register. This time we are copying register B to the indirect register. Okay, so basically the same thing. These instructions basically come in pairs. At RAM location 7, we'll write an instruction to use a load indirect instruction, which is also an instruction that the microcode is what you need to do. This is going to load or read indirect from RAM using INDIR reg as a pointer, and this time to register D. So we're going to use up all 4 registers in the register bank. Register A, register B are basically serving as pointers. Register C and register D will hold the values to be added by the add instruction. Are we doing okay so far with the specification? At RAM location 8, you're going to write an instruction. It's going to be the add instruction. So with the add instruction, I am specifying that you have to add the content of register C and register D, and I want the sum to be stored in register C. So register C is the one that is both serving as the source and the destination of the add instruction. Is that still okay so far? Okay. So now that we have everything calculated, we will then use location 9 and A in hexadecimal in RAM to write an instruction to load a value of 22 in hexadecimal into register A again. So we're going to overwrite register A with 22 as a value. And then the last instruction at location B, which is location 11 if you count in decimal, write an instruction to store. The ST instruction is already implemented, and I want you to store indirect. The value of register C has to go to the location pointed to I register A. We doing okay so far with this specification?
I don't understand that part. I'm not really understanding that part right there.
Which part?
You want to store indirect the value?
Store indirect. That instruction is already implemented. Okay, so let me kind of give you the C++ equivalence, pseudo C++ equivalence of these instructions. And I'm going to use mousepad here, just so that everything that I talk about will be recorded as well. Okay, so we'll go back to the first instruction. Okay, this is kind of like if you want to do this in C++. Now, you may or may not want to do it this way. Okay, it's equivalent to going to location 20 and store 0x56 to that location.
Oh, that's that one.
Huh?
Oh, this is that one.
No, that's the first instruction.
Oh, okay.
That's just the first instruction. Okay, so the first instruction is just setting up RAM, the content of RAM, so that we can get those locations for adding later on. The second instruction, not instruction, this is just the initialization of a RAM location. So the second initialization is going to location 21, and it's going to store the other value, which is 8A. Okay, any questions about this? Do you guys have any questions? No? Okay. So these two are not actual instructions. You're just initializing certain locations in RAM with specific values. Yep. Okay. So that's just initialization. Okay. We are not writing instructions for these two. But then after that, we're going to be writing instructions. So the third item here is actually an instruction to perform the following in C and C++. So we'll write an instruction to copy 20 in hexadecimal into register A. So I'm going to just use reg A here to represent register A. So in this case, all I'm doing is to change the content of register A to 20 in hexadecimal, nothing more than that. The next instruction is doing the same thing, but to register B. So register B is now initialized to 21, but there are no indirect whatsoever with these two instructions. I'm just changing the registers to 20 and 21 respectively. And then we move on to the next instruction. Okay. So I'm going to scroll this up. Okay, like that one. Okay, so we can now just, it's easier for us to see which instruction we're talking about and what equivalent C code we are going to use to represent it. So at RAM location 4, the instruction is to copy to the indirect register. So it's kind of the same thing as INDIR indirect register is just going to get the value of register A. It's just copying a register to the indirect register. We're not going to do any type of indirect memory access. There's no RAM access other than reading the instruction itself. Okay. And then we have the next instruction. Next instruction is do a LDI, a load indirect from RAM location, and we want to put it into register C. Okay. So I'm going to scroll down a little bit here. Now this one is a little bit special, so I really kind of need you guys to pay more attention to this one, because the destination is register C, but what it's getting is not the content of the indirect register. It is getting what the indirect register is pointing to. So,
Reg A.
Dereference,
yeah?
yeah, we got dereference and indirect.
Yes, we are gonna dereference indirect register, but not reg A, because reg A cannot connect to the address bus directly, but the indirect register can. Okay. So that's what. Yeah. Go ahead.
Go ahead.
So the indirect register, so these two registers can't connect to each other basically?
Well, the instruction at location 5 is going to utilize the indirect register so that it will specify what is on the address bus. And then what comes out of the RAM chip when you're reading it goes into register C.
Okay.
Okay?
So you're like reading.
Yeah, you're basically just reading a location
Yeah.
pointed to by the indirect register and store that into register C.
Yes.
So the fact that we couldn't dereference register A in C, would that be similar to trying to dereference something that's not of like a pointer type?
Yes. Well, effectively speaking, we are these two instructions combined is doing a reg C equals to dereference register A. But I cannot do that because of a limitation of the architecture. There's no way for me to take the output of a register of the register bank and directly hook it up to the address line.
So it'd be the same as like you have an int X. You can't. I mean, technically, I guess you could like dereference that, but that probably be problematic.
Yeah, we'll see more clearly why I have to separate these into different instructions. So the next instruction pair is going to be about the same thing. The indirect register is now copied from register B, and then register C, register D, sorry, this time, is going to get whatever the indirect register is pointing to. Okay. So these are basically like two pairs of instructions in order to read indirect into register C and register D. And then the next instruction is the add instruction, and I want register C to store the result. So it's basically the same thing as register C plus equal to register D. And then the last two instructions are for setting up to store the result. So to store the result, I am going to overwrite register A with 0x22, and then with one single instruction, I can do the store indirect because it is possible with that one. And this is going to be done by, it's going to be indirect register A, dereference register A gets register C. That's the last instruction. So these are the equivalent pseudo C instruction or pseudo C statements or operations for each individual instruction. So it might be helpful to kind of look at it this way because you know C already. If you do not, really should be taking that class again. But I'm only using a very simple dereference here. Okay, it's nothing fancy. We're not dealing with structures or anything like that. We are simply using dereferencing to go to a location, grab the content of that location, and then do something with it. Are we doing okay so far with this description here? It's okay? Any questions about this? Yep.
So, in this situation, basically, the registers, are they they're storing the addresses or the content?
It depends on how you use the register. Okay. So when you look at it first, okay, let me just go back and so I can highlight it. So if you look at this instruction here, I have no idea whether 20 is going to be used as an address or as a number to be added because it's just 20, right? It's just a bit pattern. In other words, I just want 00100000 to be stored in register A. That's all this instruction is going to do. So at that point, you don't even know whether 20 is an ASCII code to be printed later on, or is it something that I want to add later on, or is it an address that I'll be dereferencing later on? There are no types associated with the registers. Is that okay? So every register is nothing more than just 8 bits that is kind of bunched up together. Yep.
In line with that, so what we're doing, so it would be our fourth line where we first have register C. So register C ends up pointing at location 20, OX 20.
No, register A is the pointer.
Well, that's what I'm saying.
Register C is the value at that location.
Oh, okay, so we dereference it, which is source 56.
Correct.
Or whatever that is.
Exactly. So if I were to look at the side effect of each instruction, okay, so if I use the side here to represent the side effect, this is going to be important as well. See, it is very helpful for you guys to ask questions because if you ask questions in a certain way, I'm going to think of something to explain it that I may not have thought of before. So in this case, the end result is register A is going to have the value 20. Okay, that's the end result. Okay, it does not change any of the other registers. This one has the end result of A register B getting 21 as an end result here. This one will end up with the indirect register getting a value of whatever register A has, which is 20. This one will go to the location 20 in RAM and then grab the content at that location and store that into register C. So the end result is register C will get a value of 56. Because in the initialization, that's how we initialized it.
OX.
Sorry?
OX, 56?
Oh, 0x, yes. In hexadecimal. There we go. And then this one is no mystery because we are just copying whatever register B has to the indirect register. So this time it will be 21. And then this one will store whatever is at location 21 into register D. But because of the way we initialize the RAM, this is going to be 8A. So register D will end up to have the value of 8A. This is going to add the two registers and store it back to register C. So register C is going to get the sum of these two. And I'm just adding it by hand right now. So this is going to be, I think that's an E. And that's going to be a 1.
Are you ready?
I'm just adding in hexadecimal.
56 and 8.
Okay, 56 and 8A, the sum is E1. Okay, let's check. Let's check to see whether that makes sense or not.
Yes, that's 16.
So we got 56, 8A in addition.
13.
66, A is 10. So this is 16. Oh, I messed up.
So
It should be E0. Yep. Okay, so that's a 0 here with a carry. And then we have 5 plus 8 plus 1, that's 9 plus 14. And 14 is E in hexadecimal. So E0 is the correct result. Okay, so I messed up. Okay, but this is correct, okay? And then with this one, we are just simply overwriting register A 0x22. And then the last one is basically saying the content at location 22 should now be the sum, which is E0. Oh, should not use one single equal, should be using 2, because I'm stating a condition that has to be true when that executes, after that executes. Yep.
So you have to use the indirect register to extract the values, but to save them,
You do not need to, right?
You do not need to.
Yeah, well, you have to use it, but it can be combined into one single instruction because that instruction is already implemented.
Okay, got it.
Yep. Okay, so are there any questions about this stuff here? The objective of your homework assignment is to accomplish this, and I'm using the pseudo C format just so that you guys know after each instruction what would be, what is observable, what should be observable. Do you guys have any questions? Anything I can answer? Okay. So the next question, the big question is, how do we get started with this? Right?
My question.
So first one, download the file, okay, unzip it, okay, and trust me, to specify the actual instructions is the easy part, okay. Once you figure out the microcode, the actual instructions is like easy, because all you're going to do is to specify, the most significant 4 bits will be the actual opcode, the instruction itself, and then for instructions that involve registers, you just have to figure out, okay, which 2 bits do you need to specify, which register. Register A is 0, 0, register B is 0, 1, register C is 1, 0, and the register D is 1, 1. Okay, and we only have seven instructions all together. Okay, so it's not going to be, that part is not going to be the hard part. The hard part is going to be the micro coding part. All right. Well, it's kind of the fun part, but it will be the fun part if once you understand all the concepts, then it's really just a matter of figuring out how to make this work. So that means understanding the architecture is really the first thing you have to do. So we'll go ahead and take a look at the architecture. So this is logic sim. There, maybe just here. All right, there we go. Okay, so here's the architecture itself. And I'll first start with explaining why we need to separate into 2 instructions when we really just want to do a load indirect. In other words, why can't I, in one single instruction, use one register to specify the address and use another register out of the register bank to store the value from a certain memory location? Why can't I do that? The reason has to do with the input into the indirect register, which is this one here, is coming in from register out 0. So I'm already using register out 0 for that purpose. Okay, so I can't do that. Okay, I can use one single register and copy that to the indirect register and set it up so that I can access indirect from RAM. But the problem is, when I need to store the value of the RAM location back into one register, which register can I overwrite? Well, the one register that I can overwrite is controlled by these bits here. Okay, that's register input select. Okay, and when you trace this wire, it is also the same selection for register output 0. That is the problem, okay? Because I'm using the same selection bits both for specifying which register to output to the indirect register, and it's the same selection pin to control which register is getting the content from RAM, okay? Now, we can implement an instruction where you have to use exactly the same register for both purposes, okay? But if you want to have the flexibility and say, I want to use one register to specify the address another register to store the content, then you cannot do it. Okay? So that's why we have to separate that into two different instructions. Is that okay so far? All right. Okay, so let's take a look at the instructions that are involved, and we'll take a look at what components you need to take a look at in order to get those instructions implemented. So we'll start with well, this one is already implemented. Okay, there's an instruction to do this already, and so the other resource that you want to utilize, when you're ready to start with this homework assignment, is to look at the spreadsheet that is also packaged in the same folder. Text processor, and it's the ODS file, which is mcc states.ods. All right, so this is a spreadsheet. You can probably open this in Microsoft Office too. If you do not have LibreOffice installed, install it. Okay, it's free, it's open source. There's a portable version of it as well, so you can install it onto a thumb drive, and you can open LibreOffice documents anywhere you want. For those of you who really do not like to install open source software, you can go to the lab, open this in LibreOffice, save it as a Microsoft Office Excel format, and then you can use the Excel file. Okay, so there are many ways to get around this limitation if you do not want to install LibreOffice. Okay. So there are a few instructions or 3 locations already specified here. The first one is fetch, which is something that you cannot really change. Okay, so what fetch is doing is, it really is just fetching an instruction into the instruction register so that you can decode the instruction and start execution. So this is not something that you really should be overriding. The first instruction that is already implemented is load register with a constant, a particular value. So this instruction is corresponding to, okay, I'm just going to point out here, this instruction corresponds to this operation, and also this operation. So those operations can be done with the opcode 1. Okay. Are we doing okay so far with this instruction? With this instruction, how does it work? And how do we specify which register is getting the byte after the instruction itself? Well, if you take a look at because this load instruction is trying to get something into a register, so that means your register select 0 or register input select is what you need to do. And if you go back to the design here, this is the wire. So those would be bit 0 to bit 1 of an instruction to specify which register you're loading into. So that means the first instruction, which is supposed to load into register A, is going to be 0001 for the most significant bit, because that's the opcode for the load instruction. These 2 bits are not used, so you can put anything here, it doesn't really matter, because we are only utilizing one single register. And then these 2 bits will specify which register are we going to overwrite, which register is going to get the content of the next byte. Are we doing okay so far? You put 00 here for register A, you put 01 for register B, and so on. But after this, you also have to specify 1 additional byte, and that's why it takes up 2 bytes locations for each one of these instructions. So this is just whatever you want to put into that particular register. So in our case, it will be 20, 21, and 22, depending on which instruction we are talking about. Are we doing okay so far with, creating the instructions for putting a particular value directly into a register? Is that good? All right. Okay, so let's move on and talk about the other instructions. Let's take a look at this instruction here. So this instruction is really, or the equivalent of this instruction, which is the CPINDIR, copied indirect register, is really just specifying a output out of the register bank, send that to the indirect register, clock the register, indirect register, to store that particular value, and that's it. Okay. So knowing what this is supposed to do, let's go through the simulator and find out what do we actually have to do to make this happen. This is the indirect register down here, not this one. This is the instruction register. This is the indirect register down here. So what we want to do is to actuate this path here so that whatever is coming out of the register bank, which is going out here, which is also known as register out 0. So whatever bit sequence is coming out of here is going to end up here into the input of the indirect register. Once that pattern is presented to indirect register, then what we'll do is we can do the enable. So you want to do the enable first so that this register is paying attention to the D port and also the clock. And then you can leave it up to the clock pin to toggle once. Okay, so the low to high transition of the clock line after you set up the D port and also after you set up the enable is going to latch the bit pattern on the D port into the content of the register. Are we doing okay so far with that? Okay. But before you do that, you first have to, your instruction, which is going to be loaded into the instruction register, is going to decode into the register bank almost immediately. Because bit 0 and bit 1 out of the instruction register is going to be sent to this guy here, which is register select 0. So what remains to be done is to turn on the enable for that particular port. Let me find out which one it is. That one here. So register enable 0 has to be asserted. So when this is asserted and you specify a particular register, this output is going to be outputting the content of whatever register you have selected. So that part has to be done prior to writing the right sequence of the indirect register. Okay. So what you need to do now is to write down, just write it on a piece of paper, a spreadsheet, or a Word document. I would use a Word document or a spreadsheet. Use some electronic way to store that, just so that you can write it down and have a way to refer to your own instruction, so that you can convert those instructions into the bit sequence. And then from the bit sequence, you can use my spreadsheet to figure out the exact, hexadecimal representation that has to go into the ROM. Okay, so let me go. Now we can switch gear to the spreadsheet because you will need to use that. This one. Okay, so getting back to this particular spreadsheet is going to be really useful because what you can do now is to specify, okay, when do I want register 0 out enable to become a 1? Maybe immediately. I don't know. I mean, you have to decide when you want it to be a 1. When do you want? Let's see, which one is going to be useful here? Indirect register write enable. Okay, may not be in the same clock cycle. Okay, because you don't want the same clock to do two things at the same time. So maybe this one has to be off, maybe by 1. Okay. Yep.
Is that enable, which means turn to what? The 0 or because we have 3 status. So one is 0, one is 1, another is
No, the tri-state thing does not really apply here. Yeah, the 3-state thing does not really apply here. Okay, so you will have to fill in all the zeros and ones with each row. But once you fill in all the zeros and ones with each row, the last 2 columns is going to be very helpful. Ooh, I messed up here somehow. Go ahead. Question?
Oh, I was just going to ask, by taking it down to the next row, you're just representing the next clock cycle, or back over?
It's going to represent the next stage. So each stage is separated by 1 clock cycle.
Okay.
So what happens is, so each clock cycle is going to increment the microcode counter itself, the MCC, and that's why when you look at the clock signal here, this is the main clock. Whenever we have a rising edge transition, this will bump up the microcode counter, which means the next bunch of zeros and ones will now be presented onto all the various parts of the processor.
Okay. And on the spreadsheet, we see that as the next row.
Correct. Yes. But this is a universal clock. So it is the very same clock that changes the microcode counter as well as into the register, the RAM chip, and all kinds of stuff like that. Okay, that's a good question. Any other questions? No other questions? Okay, so once you specify, you'll fill in all the bits, all the zeros and ones of one row. What you want to do, and let me fix this one first. There we go. So once you're done with that, then you want to just copy and paste this equation here. If you double click on it, it will show you the equation. And you can look at the equation and probably know what it is for. Okay, it's really just converting a binary number given the individual bits back into the value that the binary number is representing. Because you can see what is one thing that what is a pattern that you can recognize with this equation here. When you look at the multiplier, the constant to each cell, they're always a power of 2, right? Do I use 2 powers of 2 twice? No. Okay. So you can definitely see that you're just using 2 to the power of 16 because I got sick and tired of typing big numbers. But we have 8, 16, 32, and so on and so forth. And there are several bits that are not specified here because those are going into the ALU to specify the operation, and those are specified by C15, and it's the least significant bits, so that's why they do not need a multiplier. Well, or they can use a multiplier of 1, which doesn't really do anything. So that's what column S is for, but it does the calculation correctly, but it gives you a decimal number. A decimal number is not going to be very helpful because when you're in the ROM editor, it wants hexadecimal numbers. So that's why we have column T. In column T, when you look at the equation, it is a decimal to hexadecimal conversion. So that's, column T is the code that you have to enter into the ROM in order to specify the microcode. Is that okay? Sort of? All right. Okay. So now that this part is done, let's take a look at the instructions that are already implemented, okay, so that we can take a look at, okay, so how do we do all of these things here? We'll start with the fetch cycle, okay? The fetch cycle is already done. You don't have to do a single thing with it, but every instruction has to start with a fetch, okay? Now, that means by the end of the last microcode of your instruction, you have to make sure that somehow the microcode counter is reset back to 0. Are we doing okay so far with that? Okay. So the question now is, but how do we do that? Yep.
Oh, well, you're about to go around to, is it the MCC CLR?
Yep. Exactly. So you can see that all instructions, not counting fetch itself because we don't want it to be an infinite loop, but when you look at this instruction or this instruction here, you can, if you look at your column D, okay, the last instruction always has a 1 here, which basically will reset the MCC or the microcode counter back to 0. So we're ready to fetch the next instruction accordingly. Is that okay? Now there's one more thing that we also have to pay attention to. It has to do with, what about the PC, the program counter? Because the program counter also has to be incremented. Otherwise, we'll be executing the same instruction over and over again, which is not going to be very helpful. So when you look at the diagram, so it really helps to kind of, when you work on this, it's going to be a little bit better because I really doubt any one of you will be using an XGA resolution monitor when you're working on a homework assignment like this one, and you have to explain it to like 40-something people and use a large zoom in at the same time. So if you use a pretty good resolution screen like a 1080p monitor, it'll be much better because you can open this up, the spreadsheet, a few other documents at the same time. So it'll be much better. But we do want to take a look at the program counter because we want the program counter to increment also. We are not really quite at the point to implement a jump instruction yet, so we're always moving on to the next instruction. So that means you have to specify this enable pin to be a 1 so that the program counter register is ready to be updated. Okay? And at the same time, you also want to make sure that this mux here is specifying the input coming from the adder and not coming from the register output. Okay? All right, so now we have to find the names of these things, right? So in that case, zooming out will definitely help, because now you can see which bit coming out of it is responsible for that. But you can also go to the spreadsheet. I try my best to use useful names for purposes like that. So when you look through these names, you will probably find it. Yep. So this is a MUX. This is the MUX input. The way I specify a MUX input is if it is a 1, it is a RAM address. Okay, this is the RAM address. It is trying to specify, are we connecting the program counter to the address bus, or are we connecting the indirect register to the address bus? A 1 means it is the first one. A 0 means it's the second one, separated by the slash. Okay, so you can see for the most part, we are using the program counter to connect to the address bus, because we're just trying to read the next instruction, or the byte after an instruction in the case of the load instruction. Only in one case we have some zeros here, and that is the instruction that can store indirect into RAM. And that's why it has to switch to the indirect register for 2 cycles in order to control the address bus from the indirect register. Okay. So getting back to reprogramming the program counter itself. So if you continue to scroll to the right-hand side, you will probably find it right there. Okay. So this is a PC and write enable, and that's also the last one here. In other words, the fetch cycle will always get ready to fetch the next instruction already. So for the most part, you don't have to worry about it. In fact, all the instructions that you are implementing do not need to mess around with the program counter, because it is already pre-incremented to the next instruction already. And none of your instructions is going to take more than 1 byte. So you don't have to mess around with clocking the program counter to increment it. I'm not sure whether I got it or not. Sometimes the pressure wave would actually knock it down, knock it out. So I just have to stomp to make sure it's a sure kill. There we go. 1 clap, 1 kill. They really like me because I'm the only person walking around doing all kinds of stuff. So I'm emitting more CO2 than any one of you. And mosquitoes hunt by following the CO2 concentration differential. So they would basically look for the sharpest change of CO2 concentration and use it to kind of guide itself to the next meal. And right now, I am the one who is, the gradient of CO2 concentration leads to me. So that's why you guys are relatively safe.
Yeah.
Sorry?
You're dancing buffet.
Yeah, they like my blood because I have high triglyceride. So if normal blood is juice, mine is like milkshake.
B1.
Sorry?
B1, they don't like B1.
Oh.
Vitamin B1.
Yeah, I think mine is more like Ensure. But for whatever reason, when I go camping, those mosquitoes don't like me. I think the country mosquitoes prefer a more
high class.
basic, down-to-earth diet.
Robust.
Yeah, more robust.
Pretentious
Yeah,
city
yeah.
mosquitoes.
Less of that, less of the ingredients that they cannot pronounce. All right, so this is all good stuff. All right, so let's go ahead and take a look at the fetch instruction cycle. And from the spreadsheet, let's figure out what it is going to do, okay? So from the spreadsheet, the first cycle, which is on row 4 of the spreadsheet, almost everything is off except for RAM selection. So that means in the first clock cycle of a fetch, it's going to tell the RAM module and say, hey, RAM module, pay attention now. Okay, I want you to pay attention right now. Let's see. It also makes sure the RAM address is connected to PC and not the indirect register. So that means, I am going to use the program counter to connect to the address bus of the RAM module, which means, the PC is the one specifying which location I'm going to read. Because I want to read an instruction, right? So the program counter is responsible to specify which instruction I want to read. So that's why that one is a 1. This is a 1 here, okay? This RAM read write is a 1, because remember, a 1 specifies the left-hand side of the slash. So in this case, it is specifying a read operation, which is appropriate because a fetch operation is trying to read from RAM in order to get the opcode. And let's see what else we are specifying here. So keep scrolling. And what else was it? Just this part here. Okay, so this is program counter select increment slash RAM data. Okay, so that is.
So the increment.
That is that's controlling, whether we are specifying the adder as the input to the mux to the program counter itself, or the RAM data going to the PC. Okay, so this is set up so that we can increment the program counter because it's coming from the adder itself. Okay, so those are the things that you have to kind of look into, when you're writing your own instruction. You don't have to mess around with the PC for one thing. Okay, so you're kind of safe there. You don't have to do anything like that. But I'm just kind of showing you, how you read the microcode of each cycle. The next cycle of the fetch instruction has most zeros here, okay, except that we have to write into the instruction register. So when you look at the instruction register write enable, that one is a 1 now. In other words, I'm setting up the instruction register itself and say, okay, I want you to pay attention to the D port as well as the clock pin. Okay. And by doing that, the clock cycle will also, overwrite the instruction register. And this is the PC write enable, which is turned on in the next cycle. It's basically saying, now it is time to actually use the incremented value of the program counter to reprogram the program counter itself. And as a result, now we are ready to go to the next location. Right. So are there any questions about the fetch cycle, which is not really an instruction, but it is a necessary cycle because every instruction starts with a fetch cycle. Go ahead.
So in our machine, basically our clock is like 1 cycle, so that whole fetch takes 4 clocks. The fetch instruction takes 4
Right.
clocks.
Right. All right. So let's take a look at the next instruction. The next instruction is load register immediate. Now inside the ROM, inside the microcode ROM, this bit pattern goes to location 10 because we have 16 instructions. So the first instruction, which is the fetch cycle, is going to take up location 0, 0 to 0F. So even though it's only using 3 clock cycles, I'm reserving 16 cycles for every single instruction. So the next one, which is the load instruction, is going to use up locations 10 to 1F in the ROM of the microcode engine. Okay? But once again, we have a very short instruction. It only takes 3 cycles. So what this one is going to do is kind of interesting. It is going to enable register write. So I'm setting up to be ready to write into a register in the register bank. I'm selecting RAM, okay? So I'm saying, okay, RAM module, pay attention now. I'm also making sure that the PC is driving the address bus. Now remember, by the time I get to this highlighted row, the program counter is already pointing past the location of the instruction itself. So it's basically pointing to the next byte already, okay? So keep that in mind first, okay? I'm specifying a memory read operation here, just like last time, so that one is not a surprise. And I'm also selecting the program counter to come, the input into the program counter is coming from the adder and not coming from the RAM data bus itself. Okay? So in other words, what I'm doing with the first step is really just saying, okay, program counter, set yourself up to be updated again. And then use the program counter to specify the address bus. And the RAM module is now set up, is selected, is ready for a read operation. Are we doing okay so far with those bit patterns? kind of. Okay. The next cycle, which is row 9 in this case, is going to specify a register in the register bank as the input register. So when you go through this, you'll see, actually it is already selected before, but this one will also enable the program counter write enable, which means, in the next cycle, the next clock is going to actually increment the program counter. And we also have to latch the content of the data bus, which is now active already, into the register. And that has to do with the memory. Oh, this is already, the write enable is already enabled here. So the actual overwriting of the register is going to happen in the second cycle. The third cycle is really just to reset the microcode counter back to the first instruction, back to the fetch cycle here, and it's going to conclude the rest of the operation. So that means with the load instruction, after the fetch, it will decode this, it will send these 2 bits into the register bank, set it up to be a register write operation, and then the program counter increments to this location. The microcode will specify to output the content of this location to the address bus. And then because the address bus is already connected to the register input or the register write port of the register bank, the clock cycle will basically overwrite whatever register is selected by the least significant 2 bits. Okay, and therefore it is going to overwrite the register with this byte here. But we also set up the PC write enable, which means the program counter is going to be incremented again to point to this location, which is really necessary because otherwise we'll be trying to read this location as the next instruction, but it's not an instruction, it is really just the content of what we want to copy into a register. So that's why with this instruction it is necessary to increment the program counter again so that we'll be ready to decode or fetch the next instruction after this one. None of your instructions require 2 bytes, so you don't have to worry about having to increment the program counter within your own instruction. Are we doing okay so far?
So we just keep the counter value there.
Hmm?
We couldn't change the counter value.
Well, with your code, the program counter is already incremented by the time it gets to your microcode, so you don't have to do a single thing about the program counter. Just don't mess with it. keep the program counter write enable 0, then you'll be fine. Yep. All right, so here's the last instruction. It is store a register to indirect based on the address already stored in another register. In other words, I'm using one register out of the register bank as a pointer and using another register as the source for the content to overwrite the memory location specified by the pointer. So with this one, in the first clock cycle, we specified register 0 output enable, which means we are setting up the register bank so that register 0 out of the register bank is now ready to drive the line, because we need that to specify the indirect register. So this output is enabled, and we will also see that the indirect register write enable is also a 1. So this completes the path from the register bank to the indirect register. Whatever the register bank outputs through register 0 will now be presented to the data port of the indirect register. It is already having the write enable specified, which means it is ready to be overwritten using the next clock. So that's the first cycle. Which register is serving as register 0 is not stated here because it is specified by the least significant 2 bits of the instruction. So that's why you don't see the selection of the register as a part of the spreadsheet, because it is just using the least significant 2 bits of the 8-bit instruction to specify which register is responsible as the output. Is that okay? What about register 1? Now, if you look at register 1, output enable is not enabled in the first one, but it is enabled in the second one. So if you go back to the diagram, register 1 of the register bank corresponds to bit 2 and bit 3 of the instruction. Okay? And that has a different path. If I go back to the architecture, you will see more clearly why this instruction is going to work out okay. Okay, so we'll go back to the register bank first and locate register out 1, okay, which is not the 0. This is the 0, and this is the 1. Okay, if you just hover over a particular node or connection point, it will show you what the name is. This is register out 1, and if you follow this thick line here, it goes to one of the inputs of the ALU. This is the ALU, and it also goes through this buffer here to the data bus. This is the actual data bus. Okay? So that means what we're doing here is we are using register out 1 to specify the data bus to the RAM module. Now, if you go back to the spreadsheet, we're also doing other things to set up the RAM so that it is now ready to be overwritten. So let's go back to the spreadsheet here. So if you kind of scroll, okay, we are looking at row 13. So when you look at row 13, it will select the RAM module. It's basically saying, hey, RAM module, pay attention now. And we'll also see that in this case, you can see that it's no longer using the program counter to drive the address bus of the RAM module. It is now using the indirect register to drive the RAM address bus, because we want the indirect register to be the one that is specifying the address. Is that okay? And when you look at the read-write, it is still a 1, which means we're still using a quote-unquote read operation, because it takes time for the content to be output to the data bus. But in the next cycle, this is specified as a 0, which means we are now specifying a write cycle, and out of the write cycle, it's going to use the indirect register to specify the address, and then the data is coming out from register 1 output, which is specified here. It is now enabled. And you can also see that there's one mux to specify which way it comes from. And let me see. I think it should be. I'm trying to find the mux control here. I think. Oh, the mux control is automatic. Okay. What I'm referring to is this part here. This is called a buffer. So when the buffer is off, it is not going to drive the output. If it's on, it will drive the output with whatever it is in input. This is the control of the buffer here, and that is the same Y as the load here. So the moment I turn this pin, the load pin, into a store, which means I'm going to switch the direction, it will also automatically switch the buffer to do the right thing. So that part is just automatic. It's tied in to the load pin of the RAM chip. Okay. And getting back to the spreadsheet, we're now ready for the last cycle. And for the last cycle, really, there's really not a whole lot to do. I switched the RAM bus back to a read operation, which is the default. I switched the switch back to here. In other words, I'm using the program counter to specify the address bus again. And the most important part is I'm resetting the microcode counter so it starts from the beginning again. So are we kind of doing okay so far with how to use this spreadsheet? Now this spreadsheet is not really just documenting the instructions that I have implemented. You should use this spreadsheet to help you implement your instruction as well. Because by specifying all the zeros and ones here, the last 2 columns will give you the value that you need to enter into the ROM of the microcode engine. All right, so with this out of the way, let's go ahead and see how we can use LogicSim to load up a program, run it, and look at the results of that program. So we'll go back to LogicSim. One thing you have to remember is the RAM module is going to be reset by the reset pin. Okay, In other words, when you're testing a program, it doesn't do what it's supposed to do, and you want to reset everything. Hitting the reset pin is going to clear the content of your RAM module. So you might want to remember to save it first every single time before you run your program, just so that you have a copy of the content of the RAM before you get started with experimenting with your code. So right here, you can do a right click on the RAM module and then click load image. And as a convention, this is not something that LogicSim enforces, but as a convention, I use a .ram extension for anything that specifies the content of RAM, and I use a .rom convention for anything that specifies the ROM. Okay. The homework assignment actually has one flaw in the description. I'll get to that part. Okay, so once I open the file, it has now loaded the instructions. So this one only has three instructions. Okay. It has no, it has 4 bytes. Okay, but I don't think it has 4 instructions. Okay, let me just right click, and if you click edit content, it will show up everything in a way that you can actually modify. And this is how you're going to program this computer. Okay, this is how you do it. You just go to each location, click on it, and then specify the content just by typing it. Like if I want to change this location to AB, that's what I type on the keyboard, just AB. Once the location is selected, then you just enter the hexadecimal code for that location. Are we doing okay so far with this? Okay. So what we want to do is now we're trying to disassemble the program. In other words, by looking at the RAM content, I want to disassemble this code and go like, okay, what is it actually doing? The first byte is a 10 in hexadecimal. So that means when you break it up into a binary number, it's going to be 00010000. Okay? You look at the most significant bits, it's 0001, which means this is a load immediate instruction. If you have a load immediate instruction, these 2 bits, the least significant 2 bits, will now specify where is the destination, which register is going to store the content of the next byte. And in this case, because it's 00, it means register A. This is basically the load instruction. And whatever 8 bits you specify next to it is not an instruction. It is a part. It's basically just the constant that you want to load into register A. So in this case, what I'm trying to load into register A is the next byte, which is 47, 01000111. Are we doing okay so far with just disassembling the instructions just by looking at it? Okay. So that means after the first instruction executes, I should expect a content of 47 in register A in the register bank. Let's take a look at the second instruction. The second instruction is a 20. Okay. Now it is a single instruction. The 08 is actually not a part of it. This is one single instruction. When you look at the table, which instruction are we talking about? We only have 2 instructions. It's the store indirect instruction, right? So the next instruction, which is 0010, this is the most significant 4 bits, is really useful. And then we have the other bits being 00 and 00. So what this means is we are using register A to specify the indirect register, which means I'm using register A as a pointer. But what am I going to store at that location in RAM? It's also register A. So I'm using register A for both purposes in this case, which means what register A has at this point, which is 47 in hexadecimal, is going to be stored at location 47. Are we okay? So we can test the program to see whether it works or not. Okay. So when you test the program, there are several ways to do it. And Tristan found this a really kind of cool way to do it by changing this clock pin here into an actual clock. Now I would do that only if you feel comfortable. Okay. In other words, replace this pin here with a clock pin like this one here. Now the reason why you want to kind of do it with care is because once you replace it with an actual clock pin, and you go under the simulate menu here, you can now select clock once, which is Control T, to perform one single clock operation. But one single clock operation includes both the rising edge and the falling edge. Okay, so it's going to go like this, and there's no way you can separate the two edges. Okay, and then the second thing is if you click on the wrong thing, which is ticks enabled, and then you change the tick frequency, then it will do it automatically. Okay, which makes it kind of hard to debug the code. Now, once you have the program almost done and you're fairly sure that it's going to work, yeah, go ahead and use the auto clock and just clock through everything. But before you're confident with that, I would still use just a regular clock pin so you have control over both the rising clock and the falling edge of the clock. Okay. So I'm going to keep the design the way it is, but if you want to change it, go ahead. So I'm going to use this clock here and give it a 1. And you can already see all the wires getting changed here. This is the fetch cycle, by the way, of the first instruction. So if I zoom out a little bit, you can now see the this is the beginning of the first clock cycle. I just have a rising edge here, and so this is the microcode instruction, all zeros of the fetch cycle, and it is now. If you just look at all the green wires, those are 1s. All the dark wires, all the dark green wires are the 0s. And when I click here, it is now selecting a location, the first location in RAM. And then the next cycle is going to put that content into the instruction register. So if I clock once here, and you can see the instruction register is now getting 1 0. And then turn it off again. And now we are ready to execute the last microcode of the fetch cycle, which is doing the decode. Now, when it does the decode, it's going to change the location here as well, because what it will do is it's going to take the most. Okay, let me zoom in so you can see better. So what the next cycle is going to do is to take the most significant bit, 4 bits out of the instruction register, combine it with 4 zeros as the least significant bits, and use it to feed into the address bus of the ROM here. So it will basically do a table lookup, and then the microcode counter will be changed to location 1 0 at that point. Then it will start to execute the microcode for the first instruction for the load instruction. So let's go ahead and clock it. Clock it one more time, and now we are ready to execute the first microcode of the load instruction. Are we kind of doing okay so far here? It's really kind of hard to look at everything because I can only show you so much of the screen when it's still kind of zoomed in.
Yeah, the last time we were talking about being able to see the other parts. If you click on, see the button that's underneath the arrow, inside like the little, underneath the menus. Look at the arrow.
Which one?
The arrow.
Oh, this one?
You know what? Up to the left.
The selection?
No, the button that's directly underneath it, to the left. Yeah. Click on that. Then click on the register to show you
nice.
what's inside the register.
Oh, very nice. Thank you, George. That's good information here. Okay, so it will show you the content of the registers. So if you double click it, those would be the actual content of the register bank at this point.
Yeah, so right now, input actually has values.
So, oh yeah, excellent. Because that's presented from the RAM bus.
Yeah.
So it is 4, 7 here, and the next cycle is going to overwrite one of the registers. In fact, we know register A is the one that's going to be overwritten.
Yeah, use version Control T if you want to do that.
Ah, nice. So we can. So this is one reason why the clock is going to be useful, because you don't have to go back to the other screen to click on the clock pin to go on to the next cycle. But if you don't do that, we can still go back to main and go to the clock pin. Now, if you feel like you can relocate the clock pin to some place that's more convenient. So I'm going to clock it here, and then do another one here. Now, if I switch back to the register, register A is now 4-7. Very good, thank you. I did not know about the feature. So this is really helpful because it gives you, basically GDB ability within the simulator. Because every step along the way, it will show you the result of executing, one of the microcode. And if you, expect something to happen within a clock cycle, and if that is not what happens, you should stop and just re-examine, okay, why is it not happening? And more importantly, exactly what happened. And then, so from that, you can debug your microcode. All right? So are you guys feeling okay with this? Especially now that we have a long weekend. My daughter in high school, really hates long weekends because she has different teachers for every subject, right? And every teacher thinks, hey, you have a long weekend, I can give you some extra homework. Okay, so with this one, the first instruction is going to be a little bit harder, okay? Because you kind of have to get used to the whole thing about using a spreadsheet, using the tool, getting down to the registers to inspect individual registers and blah 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 blah. So that will take you a little bit longer. So I would recommend just doing something light duty for the first one. Okay, you can actually implement the add instruction first, which I think is probably the easier one to implement by hard coding stuff into the registers and then just execute the instruction to perform the add. Okay. Now, by means of hard coding something into the register, simply means going into the register bank, using this particular mode as a name for that. Show simulation hierarchy in Explorer pane. Okay, so you have to select this pane first, or this particular button, and then you can go into a register and just say, I'm going to overwrite it, and just by typing something over, it's going to overwrite it. So if I want register B to have a value of say 5.6, you just type in 5.6. I have just doctored the value of a register to a particular value. So that means it is possible for you to debug and implement your add instruction ahead of all of the other instructions. And the add instruction is easier, okay? It's easier to debug as well. It doesn't involve the memory bus at all, okay? It doesn't do any type of store, indirect, and anything crazy stuff like that. So that would be an easy one to implement. The other one, which I think is easier to implement, is CP indirect, because that one only needs you to require to enable register 0 output or register out 0 of the register bank, enable the write enable of the indirect register, and just let it clock. And that's it. So for that one, you can easily inspect the indirect register to see whether it is getting the content of whatever register is copying from. And you can doctor the content of the source register any way you want, just by doing what I did a little bit earlier, and then you can debug that. And it also does not involve the memory bus, it does not involve the memory module, so that would be actually another easy instruction to implement first. So I would start with the add instruction or the CP indirect instruction first. The LD indirect instruction, load indirect instruction, is a little bit harder because it does require you to specify, I want the address bus of the RAM chip to be driven by the indirect register, okay? Because that's the whole purpose of setting up the indirect register. And then the output of the RAM has to go into the register bank to whatever register it is supposed to overwrite. So that one is slightly more difficult, but still not extremely difficult. Which other instruction do we have to implement? That's it, right? We only have 3 instructions to implement. Are there any questions about how to write the actual opcode for all of these operations? Okay, I'll give you one example. Okay, this one is actually the easy one. I'll do this one. Okay, so the instruction to this one is the add instruction. So if you go back to the homework description, the add instruction is, where is it? Up there. Okay, it's 0101 as the most significant bit, that's 5, okay? So basically you start with a 5, 0x, 5 as the most significant nibble or 4 bits of the instruction. The least significant byte is the least significant 4 bits is going to specify which one is register C and which one is register D. So I'm going to give you guys a hand here. The one register that can serve both as the output, as the and also as the input of the register bank is register 0. Okay, so that would be okay, bit 0 and bit 1. So in this case, because we want it to be C, okay, register C is 1 0. Okay, it's 2, but that's because we count from 0. Okay, and then the other one, which is register D, is going to be register 1 of the register bank. So that would be the 1 1. So this instruction together is 0 1 0 1 for the most significant 4 bits. The least significant 4 bits is going to be 1 1 1 0. So when you translate that, so that's going to be 5E as the instruction of the add instruction. Okay. That's normally the job of an assembler, but since I don't have an assembler for this architecture, unless somebody wants to write one, you kind of have to do this by hand. That would be a great project to do for the first exam. We'll implement an assembler for this architecture.
Yeah. So you're not trying to have any students at the end of the You're like, how do I manage my class?
Okay, how should I put this? When I took assembly language programming at San Francisco State University, okay, which is not well known for being super competitive or prestigious or anything like that, right? I mean, it's San Francisco State University, which is good at 2 things, okay? I think it is good at, the nursing program is good, and the business program is good, okay? But at the time that I was there, they were about to scrap the engineering/computer science department altogether. It's like, nobody wants to go through these programs. Let's just,
Oh, you mean like just
get rid of them.
Oh,
Yeah.
wow.
Yeah, but they did not. But anyway, when I took assembly language programming, it was a night class on Monday, and it's once a week kind of class. So the class went from 7 o'clock p.m. to 10 o'clock. Now you can say, but this class is the same way. We go from 7 to 10 o'clock. That's like 3 hours of lecture. Okay, we're not breaking up into labs. The professor does not go to the lab at all. There are 60 students to begin with, and this is about, oh, I forgot again. I cannot. Okay, so, no, I'll make sure that we have enough time, okay, so I'll keep yakking until you guys are done with the road. So anyway, so the class started off with 60 students, 60, okay, and we have about, I would say about 45-ish, at the time being, okay. So imagine this classroom plus 15 more students. It started off with 60 people. To do the homework assignment, now you guys have the virtual machine thing, so you can basically put it onto a thumb drive, plug it into any Windows, or Linux machine and do your homework. We had 4 hardwired terminals to a VAX 11 machine that can do the homework assignment. In other words, imagine you go to room 152 and only 4 of those computers are equipped to do the homework assignment. And none of those, we did not even have VI. Okay, VI is an abbreviation of visual, which means, hey, I can move the cursor up and down. We had line editors at the time, which means you cannot, there's no visual. Okay, you have to say, okay, I'm ready to edit line 67. And then the editor will throw out line 67 to you. You go like, okay, what do you want to do with it? I want to copy the first 60 characters and then make some changes to the rest. That's how you edit a program using that architecture.
So you guys come in with your code already handwritten, so you would know reference like where?
It depends on each individual student, okay? So I typically will try to get the homework assignment done within the first 2 days of the assignment. Now remember, this is a once-a-week class, so if I get the homework assignment description on Monday, that means I want to get it done by Wednesday, okay? And typically, when I work on my homework assignments, the lab is like empty. You can hear the cricket, like chirp, 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 right? And then 2 weeks later, because a typical homework assignment is kind of difficult, the professor gave us like 2 weeks or so for each homework assignment. So about 1 week before the deadline, some people will start to roll into the lab, okay? And then in the last 2 days or so, there'll be like a long line of people waiting for those terminals. Because remember, you have a class of 60 students. Only 4 terminals can be used to do homework assignments. And so they put a time limit of how long each person can stay on the computer. Basically it's called the, I'm trying to remember the operating system concept for that. Time slicing, that's it. It's round robin time slicing, okay? So what you do is you sign up for a time and you show up during that time, you work on the computer. After 1 hour, somebody's gonna kick you out. Then you have to enter your name as the last person again on that list, and wait that much time, come back and try to continue your the train of thought from several hours ago to debug an assembly language program. So halfway through the semester, the class dropped down to about 30 students from 60. So about half survived the first half of the semester. And then the professor, instead of teaching stuff like this, or actual assembly language programming, which he did, okay, he would also go over and talk about exceptions, virtual memory organization, and all kinds of other much more advanced topics. So by the end of the semester, we had 12 students left out of a class originally having 60 students. So 48 students, decided to either have to take it somewhere else, take it later, wait until this professor retires. And by the way, that professor was an adjunct, professor too. His full-time job was over at UC Berkeley, and he just, do a one-night gig, at San Francisco State University, once a week. But I learned a lot from that class. It was a really fun class. I learned about virtual memory. What happens? What is virtual memory? Since you guys are still passing the road sheet, I'm keeping you guys entertained so that you are not feeling bored. It's like, when do I get to the road sheet? When is it going to get to me? We learned about virtual memory. So how does it work? How many people know kind of what virtual memory is about?
Isn't it total space?
Go ahead.
It's wasn't it when it stores virtual memory is when it stores on a hard disk, right?
Right. It's a mechanism where the system can pretend that you have more RAM than you actually do. So the way it works is it makes use of the hard drive, and it basically says, okay, if you run out of memory, what happens is the operating system will look at the least frequently or the page that has not been used the longest, and say, I'm going to page it out of RAM. And what that really involves is really copying that protocol 1 page, which is one quantum of locations that you can put out onto the hard drive. So it will page it out onto the hard drive, and it will page in whatever is actually requested. So by doing this, your system can pretend that you have 16 gigs of RAM when you only have 4, but that assumes that the other 12 gigs is not going to be used at the same time when you have to use the other 4 gigs. Okay? But the mechanism to get it done is actually down to the processor. And what happens is the processor has what we call a virtual memory table as a lookup mechanism. So the operating system combined with the processor will keep track of, in actual physical memory, which page is which page in logical space. So this way, if you run out of memory and you need to page in another page of logical memory, it will update the table. But from the application's perspective, this is all transparent. So from your perspective as a programmer, you can actually think that the system actually has 16 gigs of RAM. But all of this stuff requires support from the processor. Because what happens is the processor has to be able to go to a certain logical memory location and realize it's not there. And that's called a page fault. A page fault is going to generate an interrupt. We'll talk about interrupts in this class as well, but it will generate an interrupt. The interrupt will now get the attention of the operating system, and then the operating system will go like, okay, who has a problem loading in memory? Oh, okay, it's this particular program. It wants to access that location, but it is not in physical RAM yet. So the operating system will then take over and go like, okay, fine, I'm gonna load it in. Okay, but first I have to look up, what page can be swapped out first, right? So we'll swap out something that has not been used for a while, swap in what is requested, and remap the memory. Update. Yeah, I know it's really attention grabbing. Yeah. So it will load in the page that is actually requested, update the table. So now it has the correct table of contents, right? And then once everything is set up, it will return back to the application. And then the application never knows what actually happened. It just says, oh, okay, this took a little bit longer than usual, but otherwise it doesn't really know that there's virtual memory operations involved. And all of that stuff was explained in the assembly language programming class.
Is that the same thing as like a swap partition in Linux?
A swap partition is where you swap things out of and into. So when you run out of memory, it is tied into that. It's kind of like a space where you say, okay, let's say you're working and you have a big huge pile of books, but at any particular time you just need about 3 or 4 of those. So that's basically the pile. Thank you. So that's basically the pile of books that you do not need right away. So that you can, because your desktop only has space for 4 or 5 books, but you have like 20 books that you eventually will need to get all your homework assignments done, but you don't need 20 books all at the same time. So the swap space or the swap partition of Linux is basically that pile that is sitting next to you. Yeah. All right, well.
Virtual used to be a big thing in early 2000s. Virtual memory. You don't hear about it too much anymore.
We have the RAM now.
Yeah, you guys have the, well, but if you think
Still
about the
do that.
quantity of RAM versus your hard drive space, the ratio really has not changed all that much.
They
Because
still do it.
because you have what 16, 32 gigs of RAM now, but your hard drives are up to 5 terabytes.
Yeah.
So that ratio really has not changed. It's just that people found that relying on virtual memory sometimes can slow down your system significantly. It's called thrashing. So when you are really running out of RAM and you really need all 20 books at the same time, then you'll be constantly juggling, swapping out, swapping in, swapping out, swapping in, and your hard drive indicator is just constantly lit, like it's the power indicator, right? Yep.
Get a second hard drive.
Get a RAID.
Yeah, I was about to say,
RAID.
Yeah, get a RAID.
I set it up. I had 2 hard drives. I had 1 drive with virtual memory.
I have 16 gig on my home computer. I have never seen it used more than 6.
Well, it's like back in the early 2000s.
And that's with virtual machines running too.
Yeah, like 16 gigs too, man.
60
Like,
gigs.
I mean, unless you're like, I'm gaming, I got on 2 virtual machines.
Usually Firefox.
All websites.
Firefox can cause issues because it has memory leak problems,
Yeah.
leak issues.
Yeah, because they because their memory at